All right, so today we're taking a look at logs. What do logs do? They answer these types of questions. If we had 2 raised to some x value is equal to 6, what is the value of x? Well, if we needed to estimate this, right, we could say 2 squared gives us 4. 2 cubed gives us 8. So then somewhere right between 2 and 3 should give us about 6. So if you say about 2.5, that's an awesome guess. Right, if you're thinking though about exponentials, it's not quite linear, right? So as the numbers get bigger, the x values get bigger, it's going to rise faster and faster. So in reality, we should be estimating a little bit higher than 2.5, so right about 2.6 would be a really, really good estimate, all right? But that's not to undermine 2.5, that's still a great estimate. So, to find the exact x value, mathematician John Napier in 1614 defined logarithms. We're going to let b and y be positive numbers where b cannot equal 1. The logarithm of y with base b is denoted by log base b of y and is defined as follows. So this is the important thing right here. It's saying that log base b of y is equal to x if and only if b of x is equal to y. So the whole idea is looking at what is the relationship between this equation and this equation. All right? You should first notice that the b in both of these cases is the base. So b is the base. Whether it's a log or it's an exponent, the b value is exactly the same. What you can see from here is to go from a log to an exponent, you should see that we take b, we raise it to the x power, and then it's equal to y, right? So we take this b, raise it to x, equal to y. And that is the relationship between logs. I know it looks a little weird right here, but let's go through some examples. It says rewrite each expression in logarithmic or exponential form. A lot of people like the little arrow method that I used down here. So let's start with that one. So it's saying the base of the log has to be the same as the base of the exponent. So we're going to put a 2 down here. We take that 2 and then we raise it to what's on the other side. So 2 to the 4th power. And then that's equal to the number inside of the log. So 16. Right? And we can double check that. 2, 4, 8, 16. Right? So that's 2 to the 4th power. For letter B here, same idea, right? We have 10 as the base. We take 10 and we raise it to the power on the other side, so 10 to the 1st power, right? And then what does 10 to the 1st power equal? It equals that 10 inside the log. For this one, letter C, we're going to go backwards, right? This is saying 3 to the 4th power is equal to 81. Well, if we have to go backwards, we have to remember the base stays the same. So it's going to be log base 3, right? And then the exponent went on the other side, so it's equal to 4, right? And then the inside of the exponent would be this 81 right here. And I always put it inside parentheses just to be safe, right? So log base 3 of 81 is equal to 4. Come over to the other side here, letter D, right? Letter D, we have log base 4, so we have 4 as the base. We always raise it to the thing on the other side, so to the 3rd power, and then what's that equal to? It's equal to 64. On this letter E, right, we need to go backwards again, so from exponent to log, the base always is the same, so this is log base 8. That 2 is always on the other side of the equal sign, so 2 moves to the other side. 64 goes inside of that log. And then our last example here, 9 squared equals 81. Again, log base has to stay the same, so base 9. So log base 9 of 81 is equal to 2. Okay, and that's how you're going to rewrite from exponential form to log form. The biggest thing to remember is that the base stays the same. So the base of the log has to be the base of the exponent. The base of the exponent has to be the same as the base of the log. That's always the greatest place to start for these ones. Okay, it says evaluate the expression without a calculator. Rewriting an exponential form can help you evaluate. Whenever you're looking at a log problem for the first time ever, right, it's saying what is this value equal to? You need to ask yourself, right, this is the base of the exponent. So the question is, what do we raise 3 to get 81? That's the question we have to answer. If you need to rewrite it in exponential form so you understand, right, do that. So 3 to the question mark is equal to 81, right? This question is the same thing as that equation that we just wrote right here. So what power do we take 3 to in order to get 81? We take it to the 4th power, right? So then log base 3 of 81 is equal to 4. Let's take a look at this next question, right? This next question is saying, what do we take 5 to in order to get out 1 over 125? If we want to rewrite it into its exponential form, that's 5 to the question mark is equal to 1 over 125. This 125 is in the bottom, so we definitely know that question mark is negative, right? So negative first. And then how do you get 125? That's 5 cubed, so negative 3. Next up, we have 1/2 as the base, so that means 1/2 is our base of our exponent. And it's saying, what do we raise 1/2 to in order to get 8, right? Well, we first need to flip that 2 to the numerator, so it's definitely going to be negative because we need to flip the base. And then 2 to what power? 2, 4, 8 would be the 3rd power, so negative 3 once again. Letter D here, we have 9 raised to some power gives us 3, right? So 9 raised to what power gives us out 3. Here's where, right, our radicals are going to come into play, right? So we need 1/2 to make 9 into 3, because 9 to the 1/2 power gives us 3. Log base b of 1 is equal to question mark. So this is saying, what do we raise b to in order to get 1? Well, this is kind of a tricky one, right? This one's actually testing a log property that we are about to learn right now, right? So any value, any base raised to what power gives us out 1? So the question mark here is 0. The base doesn't matter. If 1 is inside of a log, your answer is always going to be 0. Okay? And that's because of this property right here, right? Anything raised to the 0 power, right? Anything raised to the 0 power up here would be equal to 1. Another log property right here, right? We have, what do we raise b to in order to just get out b? So if the base and the number inside of the log match, the answer is always going to be 1. It doesn't matter what number b is. If they're the same number, you're always going to get 1. So these are actually two super important log properties, right? So log base anything of 1, log base anything of itself, okay? So the logarithm with base 10 is called the common log. In common log, this is what's on your calculator. So it's on calculators. That's your button, is the common log. It's denoted by log base 10 or simply log, which log is what you see on your calculator. The logarithm with base e is called the natural log. It can be denoted by log base e, but is more often denoted by ln. And I always write my ln's with a cursive L, all right? And you are always going to see it like this. I literally never write natural log like log base e, okay? It's always going to be just ln. So one thing to notice about these two definitions, the log button on your calculator only works for powers of 10. So you have to be super careful with these. You're not trying to plug in the wrong thing into your calculator, okay? So let's continue. Rewrite ln 4 equals x in exponential form. Well, we know the base on ln is the e, okay? So this is saying e raised to the x is equal to 4. And that would be rewritten in exponential form. The next one says rewrite e to the x is equal to 7 in logarithmic form. Well, log base e is ln. And then it's always, the x is always on the opposite side, so equals x. And then inside the ln, we have 7. Next it says use your calculator to evaluate log of 5. Now this log of 5, is our log base 10. When there's no number here, it's just automatically considered base 10, which is the button in your calculator. So let me see if I can find that in Desmos real quick. There it is. So log right here, boom, of 5 is equal to 0.69, and then we'll just go 3 decimal places, 9. Okay, next question says the ln of 1, or the natural log of 1. So natural log is right here in the Desmos calculator, and it's 0.1. So that's going to give us negative 2.303. Okay, and that should make sense. Why should it make sense? Because the base is e. This is asking us e raised to what power gives us out a decimal smaller than 1. Right? Well, it has to be negative because e is bigger than 1. We need to make it 1 over e at least, right? So that's the negative. And then apparently it's a squared version, okay? Same thing for this last question, right? 10 to 5, this is saying 10 raised to what power gives us out 5? That has to be smaller than 1 because it has to be a radical, right? So we have to be smaller than 1. You have to think about these like small intricate details, and that's how you're going to check yourself on these log questions. So some extra properties to note when we're talking about logs. The first one that we're going to look at is a log property. It says b raised to the log base b of x is just equal to x. So this, because b and log go together, this b would cancel with this log base b. The only thing that you would have left is just an x. All right. This can also go the other way, where if you had log base b of b to the x, this log base b would cancel with this b here, and you would just be left with x. All right. Works the same with natural log. If you have e to the ln of x, e and ln would cancel, and you would just be left with x. And then if you had the ln of e to the x, the ln and the e would also cancel, and you would just be left with x. So what's the key relationship to note here? Log is the inverse operation of an exponent. All right, so it's the inverse operation of an exponent. So this question says find the inverse of the function. Remember, you first need to switch x and y. Then, to get the inverse of a logarithm, change it to its exponential. And to get the inverse of an exponential, change it to its log. So, how do we do this? There's a couple ways to do this. I'm going to show you both ways, right? The first way, we just need to swap x and y. I mean, you always are going to start with that. So x is equal to log base 5 of y. And then you can change it to its exponential form. So this is saying 5 raised to the x is equal to y. So 5x is equal to y. And that's all you have to do. All right, swap x and y, change it to its exponential form. It's as easy as that. Okay? Let's take a look at C next here. So C, we're going to swap x and y again. So that's going to give us x is equal to the natural log of y. All right? And we're going to talk about the next thing that we're going to do. We'll talk about this more. But if I wanted to solve for y right here, I need to undo the natural log. Well, the inverse operation of natural log is to exponentiate. So just like to undo multiplication, you have to divide. To undo a natural log, you have to exponentiate both sides. So we're going to exponentiate both sides. So we're going to put an e under this x, and we're going to put an e under this natural log. What does that do? E to the natural log cancels. You're just left with y. And on the left side, you have e to the x. All right? And that's how we're going to solve these types of equations, exponentiation. I don't know if that's a word, don't quote me on it, but that's basically what we're doing. What if we needed to go backwards, right? So there's two ways you could go backwards. You could switch and make this into its log form. So we're going to swap x and y. Right? So we're going to put x equals 6 to the y. So then that's log base 6. Y is on the other side of x, right? So that's switching it to its exponential form. That's one great way to do this question. The other great way to do this question is take the log of both sides. So we take the log base 6, because that's the base here, of the left side, and we take log base 6 of the right side. Log base 6 here cancels with this 6, so you just get y. And then you have log base 6 of x. All right? And as you can see, same answer. One, we solved for it. The other, we just switched from one form to the other. So there's two ways you can do this, right? So it says use the inverse properties to simplify the expression. Hint, it may help to rewrite exponentials as logarithms and logarithms as exponentials, unless you remember the above properties. So let's try to focus on mainly the above properties right here. First property, right, was b raised to a log of the same base just cancels. So then we have 10 raised to, this is log base 10 because there's no number there, so cancel, cancel. So then we're just left with 2. Letter B here, we have log base 3 of 3 to the x. Well, this log 3 cancels with this 3, and we're just left with x. For this next one, e to the ln, e cancels with ln because e is raised to the ln, and so we're just left with xy. For letter D, this is where they get a little tricky, right? This number is not the same as the base here. In order to cancel, they have to be the same number. So then let's go through this, right? We can make 8 become a 2. Let's think about it. So we have the log base 2 of 2, and then what makes 8? 2, 4, 8. So 2 to the third power, and then that whole thing is raised to the x. So we use our exponent properties. So this is log base 2 of 2 to the 3x. Log base 2 cancels with this 2, and you're just left with 3x. All right. And then for this last one, letter E, same idea, right? How can we make 25 out of 5? So we go log base 5 of 5, but 5 is getting squared because we need 25. So raised to the x. Log base 5 cancels with 5 there. 2 multiplied by x leaves us with just 2x. All right. And that's all the notes we're going to get through for the first day. So as always, if you have any questions, please let me know and message me on Canvas. I know this log stuff can be super confusing. So if you're struggling, let me know. I need to know. All right. That way I can just work with you and we can figure